For the next block of study, we are going to talk about pipe flow. We're going to study pipe flow. And so the first step of that is determining flow regime, which is the purpose of today's video. Now, there are different types of flow. Pipe flow that we're going to study is what's called internal flow. And internal flow is flow that completely fills the interior of a conduit. If you have only a partially full pipe or an open channel like a river, that would be something that's considered open channel flow. And we're not going to discuss that in this course. There's also external flow, like the airflow around an airfoil, the flow around a boat hull. Those are external flow problems will be covered later on in a later course. So we are only going to focus on pipe flow, flow that completely fills the interior of a conduit. And this flow is caused by a negative pressure gradient or a pressure differential. So the pressure at the inlet has to be greater than the pressure at the exit. And you learn this when we derive the mechanical form of the conservation of energy. That was what that flow work was. And so you see this type of flow. This isn't as narrow of a concept as you think it is. The water pipes in your house that run water to your sinks, those are going to be completely filled conduits. Oil pipelines, drainage lines that are completely full, and say after a flood, as they're exhausting into some reservoir. Even the veins inside your body are completely filled conduits that you could model with internal flow. So let's talk internal flow characteristics or regimes of flow. And there's three regimes of flow. There's laminar flow, transitional flow, and turbulent flow. And let's look at each one of these individually. So here's a picture from your textbook of laminar flow. And you can see that laminar flow is very ordered, all the streamlines in a row. There's not a lot of mixing, there's no mixing. And so it's very smooth flow, it's highly ordered. And in this case, the fluid shear dominates, so as opposed to momentum. And we'll talk about that momentum dominating when we get to turbulent flow. Let's take a look at what this, visualize what this looks like. Here's a video I'm going to link to that we pulled off of YouTube. And this is a completely full conduit with fluid, with water moving left to right. It's completely full, and they've injected a dye there in the center, and you can see that that dye follows a streamline. It never mixes, it stays together. It's very smooth and very ordered, and I can replay that for you. And you can witness it moving from left to right. But it's very, very ordered flow, and that's what laminar pipe flow looks like. And this usually occurs at obviously very low velocities. Next, we have turbulent flow. Turbulent flow is characterized by a lot of disorder. It's random flow, it's highly disordered, a lot of mixing going on, and we have a lot of velocity fluctuations for each fluid element. In this case, the inertial forces are dominant over the shear forces. And let's take a look at what this looks like. So we're going to look at that same pipe, but this time we've increased the velocity in the pipe, so we've increased the probability of turbulence. So now you can see that dye being injected, coming out initially laminar, but once it mixes with that flow, even though you can't see it because it's water, it's clear, you can see that red dye getting mixed together in that turbulent flow. So you're saying, okay, that's laminar, got it. That's turbulent, got it. What is transitional? Well, transitional flow is a flow regime in which the flow is constantly transitioning back and forth between laminar and between turbulent. And it's kind of this very difficult to model, very difficult to analyze, intermediate switching region between laminar flow and turbulent flow. And it's one that you really want to avoid, and we'll talk about that a little bit later. So how do we determine the region of flow that we're in? Well, we use the Reynolds number. And Reynolds number is named after Osborne Reynolds. He lived in 1842 to 1912 in England. He was an inventor and scholar in fluid mechanics and heat transfer, a pioneer in fluid mechanics, and you can Google him and read more about him if you like. So what is the Reynolds number that's named after him? Well, it's a dimensionless number. It's one of the few dimensionless numbers used in fluid dynamics that is kind of one of the cores of comparing different fluids. It's used to determine the flow regime. And it's a ratio of those inertial forces to the viscous forces to see which dominates. Where inertial forces are defined as the density times the velocity of the fluid squared divided by what's called the characteristic length. And the viscous forces are defined as the dynamic viscosity times the velocity divided by the characteristic length squared. So I'll just list those down at the bottom for you, what each one of those terms are. And so if we put a ratio of inertial to viscous forces and then canceled out like terms and did our algebra and simplified, the general form of a Reynolds number, so a Reynolds number, this dimensionless number, is the density of the fluid times the velocity of the fluid times the characteristic length divided by the dynamic viscosity, which is a property of the fluid. So how does this relate to pipe flow? Well, for an internal flow inside a pipe, the characteristic length is the diameter of that pipe. So if I replace characteristic length with diameter, I can write the Reynolds number for pipe flow. That's what that subscript D, think as D is for diameter. So we can differentiate between that and a Reynolds number for external flow. The Reynolds number for internal flow in a pipe for a full conduit is the density times the velocity times the diameter divided by the dynamic viscosity. And I can write this in another way as well. If I say that I use the kinematic viscosity, where the kinematic viscosity is the dynamic viscosity divided by the density, I can write it as the velocity times the diameter divided by the kinematic viscosity. They're just two ways of writing the same thing, two different fluid properties. One's just divided by the diameter to obtain the other. And this is equation 9.2, and that's a keeper, so we're going to cloud that up in your text. So how does that help me? Well, let's go back to our previous slide where we have the different types of flow, the laminar, transitional, and turbulent. If I have a Reynolds number that's less than 2,000, then that I deem that to be in the laminar flow region. If I have a Reynolds number that's between 2,000 and 10,000, it means I'm in transitional flow. And if I have a Reynolds number greater than 10,000, I'm in the turbulent region. So these are things to note. These are keepers, and they're on your RDC as well. And we'll talk about Moody diagrams later on. They're also located on the Moody diagrams. And here's the thing to discuss. These numbers may be contradictory if you do some internet research. There's a lot of different sources that say a lot of different things. Some people say the laminar flow ends at 2,300 instead of 2,000. Some people will say that turbulent flow starts at 4,000, not 10,000. And the reality is that in that transitional region, it's kind of a function of the liquid, the fluid, and the surfaces interacting with, and it's still kind of up in the air. It's still not an exact science. Obviously, we'd like to work in laminar flow, but in order to get Reynolds numbers that low, depending on your fluid, usually it's very, very slow. And the reality is most practical application engineering problems are going to be in the turbulent flow region. And they're going to be orders of 10 to the 4th, 10 to the 5th, 10 to the 6th, so even much higher than 10,000. So that disparity between 4 and 10,000 isn't really a huge disparity in the big scheme of things. So that's something to consider. And the reality is there really is no pure numeric form of the analytic form, I should say, of the momentum equation to get an exact study of turbulent flow. And there are numerical methods, but those numerical methods also require assumptions to be solved. And sometimes they match up with experimental data. Sometimes they're very, very different from experimental data. So it's a very difficult region to study, but there are some advantages to turbulent flow. And the reality is most problems are going to be turbulent flow. I mentioned previously, just to end, why do you want to avoid transitional flow? Well, as I transition from laminar flow to turbulent flow in that region, I'm going to have huge, sometimes small, but I'm going to have pressure fluctuations. And so when I'm designing something, designing a pipe system, I'm going to design it for the forces that I'm designing it to handle, whether it's turbulent or laminar. If I'm constantly varying between the two and having pressure fluctuations, I'm going to get what's called water hammer. And it's going to cause vibrations in the pipe, which could cause fatigue failure, which could cause stresses, and ultimately cause failure in your system. So it's a region we try to stay out of. So we say turbulent starts at about 10,000. So if you're trying to plan for turbulent, try to get your Reynolds number at least greater than 10,000 and avoid that transitional region completely. This completes the video. If you have any questions, feel free to see your instructor.